Picture this. You're standing on a balcony overlooking a massive futuristic city. Millions of people rushing through the streets, every one of them constantly sending signals, gestures, messages, tiny fragments of behavior that, if captured and understood, could reveal patterns about the entire population. But now imagine that instead of a city, it's the internet. And instead of millions of people, it's billions. Every click, every login, every video play, every search query, every swipe, every tiny interaction produces a data event. Not once per minute, not once per second, but tens of thousands of times per second, from all over the world, non-stop. And what if you had to capture all of it, every last event, route it to where it needs to go, analyze it, store it, and make it available in real time? This isn't science fiction. This is the real challenge that companies like LinkedIn, Facebook, and many others found themselves facing. And out of that challenge came one of the most important innovations in modern data engineering, Kafka. Today, we're diving deep into the research paper that introduced Kafka to the world, explaining how it works, why it was created, and how it now powers some of the largest systems on Earth. Before we jump into the full story, take a moment to like this video and subscribe to the channel. It helps immensely, and it ensures you won't miss future deep dives into transformative technologies and breakthrough research. Now let's step back in time to understand why Kafka had to be invented. In the early days of the internet, most data systems weren't built for high-volume, real-time processing. Websites generated logs, simple text files containing information about what users did, when servers handled requests, and how systems performed. These logs were mostly used for offline analytics. Engineers would scrape them from servers, copy them to analytical systems, and crunch through them hours or days later to generate reports. But as companies grew bigger and more ambitious, everything changed. Suddenly, logs weren't just passive records. They became active fuel feeding critical real-time applications. Search engines wanted to update results instantly based on what users clicked. Recommendation systems relied on fresh data to determine what songs to play, what products to show, or what articles to surface. Ad systems needed instant feedback on impressions and clicks. Security teams needed immediate signals to detect unusual and potentially malicious behavior. And social networks needed to update news feeds the moment someone posted, liked, commented, or shared. The problem? The volume of this log data was exploding. Consider that even simple user actions often generate multiple log entries. A page with dozens of recommended items could generate dozens of exposure events before a single click even happens. Systems like China Mobile were generating 5 to 8 terabytes of call logs every day. Facebook was generating nearly 6 terabytes of user activity events per day. And that was over a decade ago. The scale has only grown since then. Traditional systems simply couldn't keep up with the demands of real-time processing at this scale. Early log aggregators like Scribe and Flume were good at collecting data and feeding it into Hadoop for offline analysis. But they weren't designed for real-time consumption, and they often relied on push-based delivery models, meaning the system would shove data to consumers whether they were ready or not. If a consumer lagged behind, too bad. On the other side of the spectrum were enterprise messaging systems like JMS-based solutions or IBM's WebSphere MQ. These systems were robust and feature-rich, but they came with heavy guarantees, transactional semantics, and complex delivery mechanisms that made them slow and unsuitable for the massive throughput required for log processing. They weren't designed to retain huge volumes of messages for extended periods, nor were they designed to scale out easily across many machines. LinkedIn engineers saw this gap and realized that existing tools couldn't support the needs of modern data pipelines. They needed a system that was distributed, high throughput, scalable, durable, simple to use, and efficient both for real-time and offline consumers. A system that could unify the data pipeline instead of relying on multiple, disconnected tools. Their solution was Kafka. Kafka is a distributed, partitioned, high-throughput messaging system designed specifically for log processing at scale. But calling Kafka a messaging system undersells its transformative design. Kafka blends concepts from commit logs, publish-subscribe messaging, and distributed file systems to create something entirely new. At its heart, Kafka revolves around topics, which represents streams of messages. A topic might represent user activity, server logs, or click events. Producers send messages to these topics. Consumers subscribe to them and read the messages. But what makes Kafka so powerful is how it handles storage and consumption. Each topic is broken into partitions. Think of a partition as a log file that grows over time. New messages are appended to the end. Messages within a partition are strictly ordered. Kafka stores these partitions on brokers, which are the servers that make up the Kafka cluster. This partitioning allows Kafka to scale horizontally. If one topic receives huge amounts of data, Kafka simply spreads its partitions across more brokers. If you need more read capacity, you add more consumers. Kafka assigns each message a simple offset, its position in the partition. Unlike traditional messaging systems, Kafka doesn't assign complex message IDs or track delivery status for each consumer. Instead, consumers themselves keep track of their own offsets. They decide where they left off. This eliminates the need for brokers to maintain per-consumer state, making Kafka incredibly scalable and efficient. Now let's talk about why Kafka is so fast. Most messaging systems try to store messages in memory for quick access. Kafka does not. Instead, Kafka relies on the operating system's file system page cache to keep recently written segments in memory automatically. Kafka writes messages sequentially, which is extremely fast for disks, and the OS naturally caches these writes in memory. When consumers read messages, they also read sequentially, allowing the OS to perform read-ahead optimizations. But there's more. Kafka uses a zero-copy system call called sendFile, which allows it to transfer bytes directly from the file system cache to the network socket without copying them into the application. Normal data transfer might involve multiple memory copies: read from disk into memory, copy into a user space buffer, copy back into a kernel buffer, and then send. Kafka avoids most of these steps entirely. This dramatically reduces CPU usage and increases throughput. Another elegant aspect of Kafka is its retention model. Kafka doesn't delete messages once consumers read them. Instead, Kafka keeps messages for a configured amount of time, often days or weeks. Messages expire based on age, not consumption. This makes it possible for consumers to rewind and reprocess data, something extremely difficult to do with traditional messaging systems. If a consumer has a bug and needs to reprocess yesterday's data, it can. If a new system comes online and needs historical context, it can simply start consuming from old offsets. Kafka also embraces a pull-based consumption model. Consumers control when they read data. This prevents slow consumers from being overwhelmed and allows consumers to batch their reads for higher efficiency. Each pull request can ask for a certain amount of data, allowing consumers to manage their own throughput. But how does Kafka handle distribution and ensure consumers work together efficiently? Kafka uses a concept called consumer groups. When multiple consumers join the same group, Kafka divides the partitions of each topic among them. Each partition is consumed by exactly one consumer in the group. If more consumers join, Kafka redistributes partitions. If consumers leave, Kafka redistributes again. This rebalancing process is coordinated through Zookeeper, a distributed consensus service. Zookeeper keeps track of which brokers are alive, which consumers belong to which group, and who owns which partition. When consumers are notified of changes, for example, a new consumer joins or a broker goes offline, they recalculate their assignments. They release partitions they no longer own and claim new ones. They then resume reading from the correct offsets stored in Zookeeper. This dynamic balancing ensures that load is shared fairly while avoiding the need for a centralized controller. Now let's explore how Kafka ensures reliable delivery. Kafka guarantees at least once delivery. Under normal circumstances, consumers read each message exactly once. But if a consumer crashes before committing its latest offset, it may read some messages again. Applications that require strict exactly once semantics typically implement their own deduplication using message offsets or unique keys. Kafka avoids heavy transactional mechanisms like two-phase commits, which would slow it down significantly. Kafka also incorporates safeguards for data integrity. Every message includes a CRC checksum. When reading from disk or receiving over the network, Kafka verifies this checksum. If corruption occurs, for example, due to a disk failure or network issue, Kafka can detect it and remove the corrupted messages. Next, let's examine how Kafka is used at LinkedIn, the environment where it was born. LinkedIn deploys Kafka clusters in each of its data centers. When front-end servers generate logs, they send them to the local Kafka cluster in batches. Real-time applications, such as recommendation engines or feed generators, consume this data directly within the same data center. In addition, LinkedIn maintains a separate Kafka cluster dedicated to offline analytics. This cluster pulls data from all live clusters using embedded consumers, creating a replicated stream of events optimized for transfer into Hadoop and other analytical systems. The pipeline is impressively fast. The end-to-end delay, from when an event occurs to when it is available in Hadoop, is around 10 seconds. This is fast enough for most monitoring, reporting, and trend analysis systems. Kafka at LinkedIn processes hundreds of gigabytes of data per day and nearly 1 billion messages, with expectations to grow even further. LinkedIn also uses Kafka for auditing. Producers periodically publish monitoring events reporting how many messages they've produced for each topic. Consumers then compare how many messages they've received. This helps detect discrepancies and ensure end-to-end correctness. For integration with Hadoop, LinkedIn developed a specialized MapReduce input format that lets jobs read directly from Kafka partitions. MapReduce tasks consume data using offsets, and because offsets are managed on the consumer side, tasks can safely restart without risk of losing messages or duplicating data unintentionally. To serialize messages, LinkedIn relies on Avro, a compact and schema-aware data format. Each message includes the ID of its Avro schema. A lightweight schema registry maps schema IDs to actual schemas. This ensures that consumers can decode messages correctly, even as schemas evolve over time. One of the most illuminating parts of the paper is the performance comparison between Kafka and other messaging systems, such as ActiveMQ and RabbitMQ. In producer tests, Kafka could send 50,000 messages per second when sending messages one at a time, and up to 400,000 messages per second when batching 50 messages at a time. ActiveMQ and RabbitMQ couldn't come close to these numbers. Kafka's efficiency comes from its simpler message format, lack of heavy headers, avoidance of expensive indexing, and aggressive optimization for sequential disk access. In consumer tests, Kafka processed 22,000 messages per second, more than 4 times the throughput of the other messaging systems tested. Again, Kafka's design, its use of send file, lack of per-message delivery tracking, and efficient log format gave it a significant advantage. The paper concludes with a vision of Kafka's future. The authors anticipate adding built-in replication across brokers for higher durability and availability. They also foresee Kafka growing into a platform for distributed stream processing. By partitioning messages on keys and delivering all messages with the same key to the same partition, Kafka already provides the foundation for operations like windowed counts, joins, and aggregations. A library of stream processing primitives would enable powerful real-time applications built directly on Kafka. Kafka's story is a story of elegance through simplicity. Instead of adding more features and more abstractions, Kafka stripped messaging down to its essence, a distributed append-only log. From that foundation, it built a system capable of incredible throughput, resilience, and flexibility. Kafka unified log processing and messaging, supporting real-time systems, offline analytics, batch processing, and auditing all within a single infrastructure. Today, Kafka forms the backbone of many of the world's most important data systems. And it all began with a straightforward but revolutionary idea. Treat logs as streams, and streams as logs. If you enjoyed this deep dive into the origins and inner workings of Kafka, please like this video, subscribe to the channel, and leave a comment telling us what technology, system, or research paper you'd like us to explore next. Your engagement helps this channel grow and lets me keep bringing you detailed explorations of the technologies shaping our world. Thanks for watching.
and I'll see you in the next one.